All right, so we're looking at Chapter 7, Video 2, and we're going to be looking about what do we do with the solubility information. So on the test, you will have this information. You will know which ones are the AQs and which ones are the S's because it's going to be indicated at the end with these little things like this. What do you do with this information? How does it tell us, if you go back to the very beginning when we were talking about this, how does it tell us whether a reaction will actually happen or not? Well, this is what the deal is. When you break something into its two parts, it's going to split into this part and this part, that and that, that and that. And remember this solid, it's not going to split apart. Stay stuck together. If you need to put a box around it to remind yourself of that, that's fine. I like these little slashes because I think it's a great way to just remind yourself what's going on. So look, down here, if he dissolves into water, we've written him as his two parts. This is called the complete ionic, and it just means you're writing everything as ions if it dissolves in the water. You can see here we've got this guy and over here we've got this guy. And then notice we've got our products. So we have this over here and we have this over here. And then notice that we kept this stuck together. That's how you do it. So I want to point out a few things. When you write ions, you cannot write Cl minus 2 and it be right, because that's implying that it's the diatomic species. And this isn't the diatomic species. Look at what he really is. I'm going to write him over here to the side. What this is Cu with a chlorine and a chlorine with him. The Cu is the +2 and the chlorine is the minus and the minus. He needs 2 chlorines because of that reason. So if I'm filling them all up, so those are negative chlorines right there being attracted to that copper, but there's 2 of them. And so that's why instead of saying Cl2 minus, which is what it looks like we should say, we're saying that when that goes into water, it breaks into a Cu floating around, and then a chlorine floating around, and another chlorine floating around. You see what I'm saying about it being in the water and looking that way? That's why we change it to 2 Cls. So then you're like, okay, so we take the subscript and we turn it in the front number. Okay, so that's what happened here, and that's what happened here. We put it in the front and it was a number. Okay. And there's actually a tiny error right here. Do you see this 2 right here? This 2 applies to him and to him. So when I brought him down, this should have had a 2 right there. So how come you don't bring the 3 from the O? Why don't you move that over and bring it down? Why are you bringing the NO3s as a group? It's because it's a polyatomic ion group. When you put the Ag and the NO3 in the water, it splits up so that it looks like you got your Ag floating around, and then you have your NO3 group. See, that's that group. Got your double bond. That whole group is negative. It's still staying stuck together. It's just separated from the Ag. Got it? Maybe? If you start to get confused, there is kind of a check point, and that's one thing that caught me on my NO3s, because on the right I had 2 NO3s, and on the left I should have had 2 NO3s. All of your coefficients should be equal on both sides. So the complete ionic right here, which you can then do, once you've done that, I'm going to change to like a green, but this is what we're going to do is we're going to cancel things that are the same. So you'll notice that I have a copper and a copper. They're the same on both sides. They both are dissolved up. That means they are not making a salt and they are not involved. Now I'm going to change and I'm going to cancel out my NO3 groups because they also were not involved. But I'm left with something on the left that is not the same with the thing that's on the right, which is good. And what that gives us is our net ionic equation. So our net ionic equation comes from this and this making this. And you may have caught the other error too. Should have been a 2 in front of that. All the atoms on the left should be equal to the atoms on the right. So it's kind of like a little self-check. Now when we write this, we don't like to have everything with the 2 subscripts, right? So you want to then rewrite it if you ever get this. And a lot of times it doesn't turn out like this. you want to rewrite this as Cl minus Aq plus Ag plus, that's a Cl, and that's Aq goes to AgCl solid. You want it to be in the lowest ratio right there. That's how you do these. You split them apart based on their AQs or not, and then you cancel out everything. So this is called the complete ionic, this is called the balanced molecular, and this is called the net ionic, like, you know, your net finances or everything. Once you take everything out, it's what you got left. Now I'm going to do the second example, and then we'll have a ton for you to practice. So AQ, this one splits here, this one splits here, this one splits here, and this one splits here. Have him here. I'm going to need a 2 in from the chlorine for him. I need a 2 in from the Na, and don't forget that that 2 also applies to the Br. So 2 Nas, I got 2 Brs. Right here I've got 2 Nas. Remember, it applies to the chlorine also, so I got 2 Cls. And then I have a Ca, and I have 2 Br minuses. So that's the complete ionic, and that would be the answer for something complete ionic. Do a quick check and just make sure that you do have all the same coefficients on both sides. This is usually the best way to do it. Sometimes, if you don't like writing all the phases at once, I'll go back and do the phases at the end. So you've got your Ca cancels with your Ca, same coefficients. And then you've got your Cl cancels with your Cl, same coefficients. And then you've got your Na cancels with your Na, same coefficients. And then you've got your Br cancels with your Br. Uh-oh, who are the spectators? I didn't mention that up here. The spectators are the ones that you canceled out. The NO3 and the Cu up here. And then over here, everyone is a spectator. Well, what? Oh, no reaction. So here's the thing. In this top example, the reaction went because it made a solid. That is proof that the reaction had the right kind of entropy and enthalpy to occur. And that's why you made a solid. And the next example, there's no reaction, because what it's saying is as soon as you dissolve those in the water's kind of holding all the pieces apart from each other, and none of them are strong enough, and none of them have strong enough, I guess, affinity for each other to try to overcome the water and to join together and do a reaction. So this is why making a solid or making something on the right-hand side is evidence that everything is in order and a reaction will actually occur. Whereas if you have nothing, everything cancels, then that's a no reaction. All right, so you go ahead and do the next few examples all the way through the end of the section. I have several examples for you to practice through. I think I've got 6.